Okay, so welcome to the second video in the proof of the fundamental theorem of calculus for the Riemann integral. So basically, in the proof, what we've done is we have started off by saying let f be the let big F be the antiderivative of little f, and then what we're going to do is investigate this quantity f of b minus f of a. What we've done is we've asserted that it's equal to this, where these are the points of any dissection you want. So you give me any dissection, I can write f of b minus f of a as this, where these are the points of the dissection. And then what we're going to do is we've used the mean value theorem to assert that we could replace this here with the f prime of yi, which, because this is the antiderivative of f, is f of yi times this quantity here, which takes us to something very similar to the definition of the upper and lower Riemann sums. So we take this sum here, let me just get it in view. I is equal to 1 to n of f of xi minus f of xi minus 1, and what we're going to now, and that's equal to f of b minus f of a, and we're going to replace this now with I is equal to 1 to n of little f of yi times xi minus 1, where yi is an element of xi minus 1 xi. We don't know what that value is because the mean value theorem doesn't tell us how to find the value, it just shows us that it exists. Okay, so f of b minus f of a is therefore equal to this great big sum here. I is equal to 1 to n of f of yi xi minus 1, and that's for any dissection you choose. You can make this. Now, this value here is right, so you can see that this is similar to the definition of the upper and lower Riemann sums, but instead of having the supremum or the infimum of f over the values within this interval, so let me just remind you of the definitions of the upper and lower Riemann sums. So the upper Riemann sum over the dissection of f would be equal to the sum from I is equal to 1 to n of this value here, the length of the interval, times the biggest value possible that f of x takes on the interval, xi minus 1 xi. Instead, we've just taken this random value. It's not necessarily the biggest value, it's not necessarily the smallest value, f of x. So what can we say about this value here? That it is less than or equal to this. So we could put in up here that it's less than or equal to the upper Riemann sum over that dissection of f. And the lower Riemann sum is defined to be equal to the sum from I is equal to 1 to n of xi minus 1 of the infimum of x is an element of this interval, and it's the infimum over all values of f of x that f of x takes on this interval here. So this is going to be less than or equal to this. And that is true, so now we could replace this with f of b minus f of a, because that's what that was equal to. And now this is true for absolutely every dissection. You give me any dissection, and this relation is true because because for any dissection I can express f of b minus f of a as this over this dissection, and this is less than or equal to this and greater than or equal to this. Therefore this, for any dissection, this relation holds. Therefore it's less than or equal to all upper Riemann sums, and it's greater than or equal to all lower Riemann sums. It is therefore equal to the f of b minus f of a from this side of this equation, because it's true for every dissection. It's therefore equal to the supremum. Oh, sorry, no, it's not necessarily equal to the supremum. It is therefore an upper bound. F of b is an upper bound. We don't know it's the least upper bound. It's an upper bound for the lower Riemann sum, so that should be a little s, of d of f, and we also know that its lower bound is a lower bound for the upper Riemann sum over dissection of f. Once again, we do not know that it's an infinum. We do not know that it's the greatest lower bound, because this doesn't tell us that. The condition that tells us that it's a lower bound because it's less than or equal to every single element of this great big set, where we consider this the set of for all dissections. You give any dissection, calculate this value and put it into a set. It's less than or equal to every single value in there, therefore it's a lower bound. But we don't know it's the greatest one. There might be a one that is greater than it, which is also a lower bound. However, because we know that the only point that can possibly satisfy being an upper bound for this, if we imagine, if the Riemann integral exists, then the lower Riemann sums are here, and the upper Riemann sums are here, and they meet. They meet here. So anything that's a lower Riemann sum, a lower bound for the upper Riemann sums is over here. It has to be less than or equal to all of these, so it has to be over here. But it's also an upper bound for all of these, so it has to be over here. And there's only one point that it can possibly be, which is the intersection of those two, which is this value at the centre. Therefore, f of b minus f of a has to be equal to the integral from a to b of f of x dx, and that is the proof of the second fundamental theorem of calculus, the way that you integrated for probably 2 years of your life when you were first exposed to calculus. That is the proof of it from this foundational definition of integration that Riemann came up with. Thank you. In the next video we will discuss the first fundamental theorem of calculus, and then we'll go on to using the second fundamental theorem of calculus to prove integration by parts, which is pretty trivial to prove. In fact, you can probably try and prove that yourself. Imagine that the antiderivative is f of b times g of b, and then work out what the value in here would have to be. You get integration by parts. Integration by substitution is a little bit more subtle, and we'll also prove that from this definition. And then we'll go on to the second theory of integration, the better, more grown-up theory of integration, which is the Bayes integration.